Alright, so we're going to pick up where we left on the last video, which is taking a look at absolute value functions. So we're going to pretend that we can't see this graph right away and that we don't see our the immediately answer to where this point is from the table. So let's take a look at this as if it were two lines. We're going to look at it from the negative slope side and from the positive. So let's find the slope of the negative. We're going to get 7 and negative 2 as our y2 and x2, and then 5 and negative 1 for our y1 and x1. That's going to end up being 2 over negative 1, which is just negative 2. And we see that is so. And let's try from the positive side. So 3, 2, and 1, and 1. So that's going to be 2 over 1, which equals 2. Again, we can see that that is true. So we know that from looking at the values that this is weighted towards the right. So it's going to be our negative slope that hits the y-axis. So we can find that point. So negative 2 is our slope. Let's plug in one of these values. We got 7. And then for the corresponding x, that's negative 2. And we're looking for this b. So that's going to be 7 equals 4 plus b. 3 equals b. Good. So we see that our y-intercept is there. We can also see it from the table. We didn't have to calculate it, but like I said, we're going to pretend like we can't see everything right off the bat. We can also see where this would have hit the y-axis. It didn't, but we can pretend that it did. So that would be 3 equals 2 times 2 plus b. And that's going to be negative 1 equals b. So what we can do then to find this point, we can actually solve this as a system. So if we have y equals negative 2 x plus 3, and we have y equals 2x minus 1, we can set these equal to each other. Y equals y, therefore this must equal this. Negative 2 x plus 3 equals 2x minus 1. Let's move this over here. So we're going to get 3 equals 4x minus 1. Move the 1 over. 4 equals 4x. 1 equals x. So when x equals 1, we have our point where they reflect over. And then we can actually come up with our absolute value from that. We know that it was shifted over and up. Well, I guess we don't know up yet. We could plug this x back into our actual function, which was the negative slope. So y equals negative 2 times 1 plus 3, y equals 1. So when x equals 1, y equals 1, and we know that that's the point at which the absolute value has a reflection. So if we wanted to make this function, we know that the slope is 2. We know that x is shifted to the right, And we know that it was shifted up 1. And we're good to go. Now, on another note about this, if we have this function here, we can actually solve that as well. So we came to our solution already, but if they're asking you to solve an absolute value, this is how we would go about it. 2x minus 1 and negative 2x minus 1. Either one of those can be inside the absolute value and come out being the same, so we have to plug them both in. So plus or minus, and for this we're not going to look at this plus 1 at all because we don't care. We just want to make sure that we know where this point is on the graph, and we can solve the function out to get it. So this will end up being 2x minus 2 equals 0. And that is going to end up being x equals 1, right? So move the negative 2 over, divide both sides by 2, x equals 1. Do the same thing here, negative 2x plus 2 equals 0. Again, move the 2 over, we get negative 2x equals negative 2. Divide both sides, and we find that x equals 1. So we came with the same answer. We found that the answer is x minus 1. So just another way of finding this point. And with that said, we can continue on to the next function, which is roots. So if we go back to our study guide, square root function. So find the starting point of the graph. Note where we go undefined in a table. That points to that point, that starting point is going to tell us where C and D are, as the root function starts at 0, 0 by default. And then next we can just plug in any x and y value, or x and y coordinate of any of the points on the function to solve for A. So let's give that a shot. If we go back to Desmos and have these become visible. So we see that the function starts at 2, 1. Right? It can't go beneath that point, so it's undefined. We can see that both in the table and on the graph. So with that said, we have our y equals some value root x minus 2 plus 1. And then we can plug in any values to find our a value. Obviously, we should not plug in 2 for x because then it's going to become 0 and we won't know. Let's try 7. A square root of 4 minus 2 plus 1. And then we can move the 1 over, so that's going to become 6 equals a root 2. 6 over root 2 equals a. So then our final function would be 6 over root 2 square root of x minus 2 plus 1. And again, like that's not exactly what it says here, but if we show, put it on here and we'll plug that in and see if it did it correctly. Y equals 6 over square root of 2 square root of x minus 2 plus 1. And we see that we are correct. That worked out just fine. So we can get rid of those. And next we're going to look at quadratics. I know we work a lot with quadratics as far as using the quadratic formula and vertex form, but if we're not given this vertex form to find this stuff, what do we do? We have to make that visible. So first of all, we can test if it is a quadratic by making sure the second difference is the same. So 50 to 50, 194. So the difference there is 48. Negative 48, 44. So the difference between 48 and negative 48, that is going to be 96. And the difference between negative 48 and negative 144 will also be 96. So we've proven that this is a quadratic, but what do we do with that information? So if we know this point, if we can see the vertex, well, then we can just plug into vertex form, and that's easy enough. So f of x is equal to, so it's 1, 2, a x minus 1 squared plus 2. And then we can plug in a value for f of x and x to find our a. We don't want to plug in this one because that will end up zeroing this out. Let's try 50 and 0. So 50 equals a, and then 0 minus 1, it's going to be negative 1 squared, is just going to be 1, plus 2. Let's move the 2 over. 48 equals a. So if we take a look at this, we see that we are correct. The other way is going to be a little more difficult. So if we don't see this transformation in the table or the graph and can then go to vertex form, there is ways to look at the table and kind of do what we did with the second difference, but what we're going to do is look at this as a system of equations. So if we set this up, we have y equals, or I'm sorry, 50 equals, so we're going to use this point right here to create our first equation, equals a x squared, so that's going to be 2, plus bx plus c. So this is just our standard form, and we plugged in y and x. Next we can plug in 2 equals a 1 squared plus b 1 squared plus c. And a third point, 50 equals a times 0 squared. Clean that up a little bit. Plus b times 0 plus c. So we got lucky in the sense that we found a point with 0 in it. But had we not done that, it would still be 3 equations with three variables, or actually 2 when you actually cancel out the c. So the c's cancel right away, always, because there's no integer in front of them. But this time we got even more of a fortunate scenario because we learned that 50 equals c right off the bat. With that, we can plug it into one of the other equations. So let's plug into this one right here. We've got 50 equals 4a plus 2b plus 50. And then those 50s are going to end up canceling each other out. 4a plus 2b. Move 4a to the other side. Negative 4a equals 2b. And divide by 2. So b is equal to negative 2a. And now we can substitute that into our third equation. 2 is equal to a plus, I guess, minus 2a. So we're substituting in for b. Minus 2a plus 50. So we can move this 50 over. Negative 48 is equal to, and then a minus 2a is going to be negative a. And we find that a is equal to 48. Let's see if that is correct. It is. So A was 48, C was 50. Oh, and I apologize, we didn't solve for B. But if we plug in 48 for A, negative 2 times 48 would be negative 96. So that works out just fine. So hopefully if they give you a problem like that, you can see it in vertex form. That's way easier. But if you do need to, you can solve this via a system of 3 equations, 3 variables pretty quickly. All right, and then lastly, let's go over rationals. So if we go back here, take a look at rational functions. Given the different types of rational functions that could exist, you're really not going to see much of them, or they're at least not going to be very complex, and they're pretty much always going to be in 1 over x format. So you're going to take a look at asymptotes and holes and whatnot to see if you can figure out what's going on. So if we go back up to where we speak about that, which is right here. So we're looking for these vertical asymptotes where we set the denominator equal to 0 and solve for x. So let's start there. If we visualize this, so what do we have here? It looks like we have a vertical asymptote, right? We can't go past this point. And we define vertical asymptote as setting the denominator equal to 0. So if we set the denominator equal to 0 and it came up with an asymptote of 2, well, then that must mean that there's an x minus 2 in the denominator. So we're already doing pretty well. Actually, let's give that a little more room than that. So there might be an a value here. And we know that this is x minus 2. Okay. From the graph, we can also see that as x is getting smaller, y is growing, but it looks like it's only approaching negative 2. It never is really reaching it. And then when we look at x growing, then we also see y approaching negative 2, but not actually getting there. So we can say that there's probably another asymptote there. Well, how would we create that situation? We could have a 2x to match, right? So if we go back to our study guide to see how we would find this. So if the highest power is in the same, then you divide the leading integer of the numerator by the leading integer of the denominator. So if we had one at 2, or sorry, -2, then that is what it would have to look like, right? We have to have the same x power to cancel and divide the numerator integer by the denominator. But if we do that, that would also flip the graph over the axis. As we can see, that doesn't really make any sense. As x is growing smaller, y is getting larger. And then when we're over here, we have when x is getting smaller, right from this side, y is getting a little more, or is getting bigger. So it's going like this. If we flip it over the axis, let's just visualize that real quick so you can see what I'm talking about. If we put in this idea, -2x over x minus 2, it would be flipped over the axis. So yes, we have that asymptote, and that works out, and yes, we have this one here. However, the values in the table and the values in the graph don't really make sense for having a flip. So that's not a possibility. Well then, if that's not what's happening here, then how could we create this asymptote? We don't have another way of getting to that point. Well, we could have a horizontal asymptote of 0 and then shift it. So let's see what that would look like. If we had the highest power in the denominator to create a horizontal asymptote of 0, then couldn't we shift down to create that scenario? So let's see what that looks like. This seems to be a fairly realistic interpretation, but we gotta check our work. A -2, and we see that we are right on the money. So if we go back here, you'll notice that we actually had a 3 over here and a 4 down here. So that fraction is going to almost equal 1. So we didn't actually find the rational function, but we got really close. So if we have 0.75 over x minus 2 minus 2, I mean, these graphs are remarkably close together. So we did pretty well. And with that, that concludes looking at functions as graphs, tables, and function notation.